Hello students, welcome to the lecture. In this chapter, we will study the systems of linear equations. By that, we mean we will study how to write the systems of linear equations, what are they, how to solve them, and in solving them, how to solve using different methods. Okay, the usual algebraic what we call the elimination method, and more importantly, our main focus will be on solving using matrices. Okay, so that means we will be studying the matrices also. Okay, we will study some introduction to matrices, some operations on matrices, and how to use matrices to solve equations. And we will be looking at some applications as well, some real world problems that can be modeled using linear equations, and we will model them and solve them. In that process, and that reminds me, we will also be interested in how many solutions does equations have. Okay, sometimes they may have only one solution, sometimes there can be more solutions, sometimes there is no solution. Okay, all those situations, how to identify, and how to write solutions, all of that will be the goal of this chapter. Let me begin with the first lesson in this video for this chapter, which would be the augmented matrix forms of uh, linear equations and some row operations that we do on these matrices, which will be used to solve the equations. Okay, so here I begin. Um, okay, right now you might be wondering, we are directly getting into a little advanced part here, the augmented matrices and row operations. What about just the linear equations and how to solve them in a simple way first, right? That will be done, and in my first video where I'm going to be solving problems. Okay, this is the lecture slide video. After this, I will be making a video where I will be starting to solve problems. Not one video, a number of videos, and in the first of them I will solve equations in the normal in the high school way, I would say, the elimination methods without using matrices. At this level, this is a college level course. We don't need to cover that in the regular lecture. Okay, but I will cover them in solving problems. Okay, let me begin here. The outline is we will be looking at uh, the diagonal form of a system of equations, and then we will be studying some row operations once you write that system of equations in a matrix form. Okay, and that will lead us to the concept of this Gaussian elimination method, which is a sophisticated method of solving equations. And in this slides and in this video, we will only get an introduction to it, the idea of it, and maybe a simple example. We will be doing more of that in the next video. Okay, and the that concept will also in the process we will be also be discussing the matrix form of an equation. Okay, so let us begin. Diagonal form of a system of equations. What is it? Suppose you have a system which has three variables, like this example here, and your three equations are the way they are written. Isn't that the best? Right? You have the first row with only x, the second row only with y, third row only with z. And one variable appears in one equation and only one variable appears. Okay. Each variable appears in an equation. There are two things there. Sorry, I took a second to read the sentence myself. So every variable of that system should be in one of the equations, and every equation has only one variable. it says both the things. So basically what that means is you will have as many equations as you have variables, and each equation will give you the value of one of the variables, basically, right? That is the diagonal form. And that also important thing is we are not writing like y equals to like something there and then x equal to something there. Okay, we are not writing in that style, zigzag. We are writing in a way where the first variable is on the top left, then the second variable, the third variable, visually also. Okay, it may you may say, now how does it matter? I could have written it like right, like moving it a little bit to the left or right, doesn't matter. It will matter very soon when we are going to convert this into a matrix. Okay, so the diagonal thing, keep that in mind. Now we are going from top left to bottom right. Now this is the end of your solving the equations, right? So at this time, I already know the values of all the variables. There is nothing to solve here, which is always the goal. Okay, in any system of equations that you construct or you are given, this is our ultimate goal. That's the point. Okay, this is the end goal of solving, you know, any linear system. Okay, that's the diagonal form. Okay, so how to get a system into the diagonal form? That is where the elementary row operations come into picture. Now, when they are not in diagonal form, for example, if I give you an equation like x plus y equals 3y minus 2g equals 7, something like that. Okay, and y, sorry, let's say x plus g equals 5. Suppose if I give you equations like that, that is not in the diagonal form. So from there, starting from such a system, how do you get the diagonal form? For that, we need the elementary row operations. Okay. Um, what do we do in this elementary row operations? It alters the system but does not change the solutions. Okay. It means we will manipulate the equations. We will add the equations, subtract the equations, or equivalent of that. We will not be writing the variables. We will only be actually writing the numbers, the coefficients. The equivalent, the effect will be adding, subtracting equations, but will not change the solution of the system, of course. Okay, the goal is to find the solution of the system. And what is the often, okay, they're often used to transform the system of equations into diagonal system. The word often is used here because later you will see the same technique, elementary row operations, will also be used to find what is called the inverse of a matrix, which is again then used for solving equations and other applications. So elementary row operations, the first introduction to us would be to convert a um, system of equations into diagonal form, but we will also use for other purposes later. Okay, so very important. What I am trying to say is very important, and so you need to be very focused in learning the techniques correctly. Okay, the first row operation. So there are three basic row operations. The first of them is interchange any two equations, any two rows. Okay, just interchange, like write one on top and the other one below, switch their places, as simple as that. Here is an example. Okay, you see those three equations written there. Only thing we did is we took the third row to the first row and we brought the first row to the third row. And how it is written, look at the notation. Okay, I don't suggest that you don't have to put those brackets around them. When you write, you can just write R1 and R3. It will be understood. Okay, that two-sided arrow indicates that we're interchanging. No, R1 goes to the place of R3 and R3 takes the place of R1. Okay. We are writing this as equations for now. Later we will be doing this in matrices also. It's the same. It is the very equivalent uh, step that we will be doing in matrices. Just keep that in mind. Okay. All right. What is the second row operation? Multiply an equation by a non-zero number. So there is a equation. And why do we do that? Sometimes, oftentimes we do that so that I can cancel some of the variables later on. Okay. It is generally this is an intermediate step to do something else later, which will be to get rid of a variable. Okay. But in this step itself, we just multiply a row. Here is an example. Take that equation and you are multiplying the first row by 1/6. Okay, 1 over 6 R1. Again, when we write it, we will just write 1 over 6 R1. Okay, multiplying by 1/6. And what does it do? It makes this coefficient x. Then you can use that multiply by 3 or something and subtract and make this become 0 later on. Okay, this is always an intermediate step. And one important thing here is you cannot multiply only the first element. Okay, when you multiply a row, the reason they are called row operations is you apply the same action on the entire row. Okay, um, just be aware of that. Row operations, focus is on the row, not just one element. And the third row operation is change an equation by adding it to another equation. I would not even say multiple, that multiple part is already taken care in the second row operation here. So let's say, that you have done already. So this operation is basically adding two rows. Okay. So you have one row, let's say, and you are adding the another row, R3. And, if you wanted to multiply that R3 by 2 first and then add, you can combine them together and write like that. Okay. That is the third row operation. So here is an example, and what I was saying earlier, the x is now missing. After that operation, you can see that x is missing from the second row. That is because you subtracted 3 times the first row from the second row. Usually that's what we try to do. Okay, we try to eliminate variables one by one. So you can see that it's getting in the diagonal shape, right? That is the intuition. Okay, the diagonal form. So what is the operation here? Multiplying the first row by 3 and subtracting from the second row. R2 minus 3 times R1. Okay. All right. Gaussian elimination method. Having seen those 3 row operations, now we are in a position to um, introduce this method of converting to diagonal form formally. Okay. What do we do? You write the systems of linear equations and apply the row operations repeatedly so that you get in the diagonal form. And what could we do? Rearrange the equations in any order, multiply an equation by a non-zero number, change an equation by adding it to a multiple of another equation. Basically, the 3 row operation, right? We will, mimic this um, in matrix form and get the solution, get it in the diagonal form. Let us see an example. say, we had obtained this previously, okay, after doing, r1 minus 3r, r2 minus 3r1, we had that matrix there, that equation. Now, what is remaining to do in the diagonal form is two things. At the main, outset, you need to get rid of the y here. So you have x, y, and z in the diagonal. That will be the diagonal. And after that, you will also get rid of this. So the ones that I circled, we need to remove them, right? Then it will be in the diagonal form. So what do we do first? Um, Now, here is the thing, okay? Good news is you don't have to follow exactly the same process that somebody else or follows. Okay, two people could do this in different sequence of operations and get the same end result, which is good because it gives you freedom, right? As long as you're moving in the right direction. Why do I say that? Just now, if you see here, what the authors of these slides have done here is multiply this row, second row, I'll zoom in and show you here, by minus 1 here, right? And the reason probably they're thinking here is, if I multiply with minus 1, it will become y like here. And then you can subtract that from uh, then you can subtract that row from the third row. So this will go to 0, right? That's okay. No? Or what you could have done instead is, or alternately, I would say instead, is you could have just added R3 and R2, second row and third row. Where? Here. If you have added R3 and R2, y and negative y would have cancelled, and in the third row, okay, that element would have become 0 here. This would have become 0, right? But as I said, you can always follow different paths, okay? So multiplying by negative and moving. So first the multiplied the second row, and again, like, you cannot just multiply that negative y, you also have to multiply that the rest of the row. So this becomes negative, that becomes negative. Okay, the change of the sign. Note that. And then what is the next step? Now you add third row and second row. Okay. Um, Not add, basically they are subtracted. What they did is effectively R3 minus R2. This is a complicated way of writing. Okay. They subtracted the second row from the third row. Okay. And what does that lead to? When you do that from the third row, if you subtract the second row, now some of these works you have to do maybe on side as a scratch work. Okay. So let me clear the annotations that I did, and I will focus on one thing at a time. Say this, y minus y, and that cancelled out. That's good. We're done there. That is easy, right? But if you do the other part here, this part, okay, it is z minus 3 over 2 z, and that will become 5 over 2 z here. Now that, if you don't see it immediately, you might want to do that on the side. So you're doing z minus already negative 3 over 2 of z, right? Then you take common denominator, this will become z plus 3z over 2, um, multiply by 2 and 2, up and down, so they have common denominator, so that becomes 5z over 2, which is what you see here. You can do that work on the side or use a calculator where you need. Okay. And now we have the diagonal part taken care, almost. Okay. And there is a small that 5 over 2, to get rid of that, we will do almost there, but we still have this part to go, right? So what do we do next? First, you have this 5 over 2 here. You convert that, you need to make it 1. So you multiply by 2 over 5. Okay? Which one? The third row. And that gives you now g. Okay? And then the next two steps would be, you can do it in a single step if you want. Add multiples of this third row to the second row and the first row in such a way that it will become 0. Okay? And you can see that here. So for example, you could do R2 plus 3 over 2 R3. Okay, because there is negative 3 over 2g here, so you add plus 3 over 2g. Similarly, for R1, you could do R1 plus 1 over 6 R. Because you have negative 1 over 6 there, you add plus 1 over 6 R3, and that will become 0. But when you do that, you will make sure that you do the same operation on numbers also here. Okay, let's see it being done, and then I will get into other things. Okay, again, as I said, the slides here have same thing but a little differently done, which is oh no, not differently done. I'm sorry. The way I was saying, they did one at a time. I was saying both operations in single step, but it has been done here one at a time. Okay, first the second row, you add 3 over 2 times the third row, so that vanishes now. And then similarly, you add 1/6 of the first and the third row to R1, and that vanishes. Right? Now you have purely x, y, and z in the diagonal form. Hence, you can say that is your solution at this point of time, x, y, and z here. Okay, and you can write your solution in the tuple like that, and the order is always understood. It's x, y, and z. Okay. Now, we did all that work, but directly on the equations. And one thing we noticed there is we are writing the equations again and again, and the variables x, y, z again and again, right? The matrix form is we try to make it more condensed now and just not write variables, write only the numbers. Because after all, if you're adding like x and 2x, your result is 3x, right? What if I had a system where I just write that as 1 and 2 and I'm adding them and the result is 3? But in my mind, I know that that is 3x. If the variable has a particular position, we can understand that it's in the background and not write it explicitly every time, right? That's what we do in the matrix form. Okay. So it is often easier to do the row operations if the coefficients are set up in a table, in a matrix. Okay. So that you are not writing the variables, just writing the numbers in a table, which will be called a matrix. Then in such a table, in such a matrix, every row is an equation, right? For example, this I will show and illustrate with an example. Okay. For example, the first row here would be 1, negative 1 over 6. There is 0 in between. There is 0y. And I will draw a line here to indicate the equality, a vertical line. Okay. And half here. Now that row will represent that equation. Why? It is 1x plus 0y in that row. Okay. Interpret that row. It is 1x plus 0y minus 1 over 6g equal to 1 over 2, right? So we can only write the coefficients and interpret that as the equation. That's what we mean by saying each row represents an equation. Okay, each row represents an equation. Then what does each column represent then? Now a matrix is a rectangular array. You have numbers written like that, but that will also create the columns, right? There is a first column, second column, third column. The column would represent the variable's position. Okay, so every column will correspond to one variable. Okay, again, going back to our previous one. Here, when you convert it into matrix form, when the other rows are also converted, this column would be for X. The second column will be for Y, third column for Z, and then there is that line which is for equality equation. And after that, that column would be for all these constant numbers on the right side. So every column will have its meaning. Okay. Um, such a table, okay. Except the last which represents the constants. Okay. Every column is represents the coefficients of a particular variable, except the last one, which is the right hand side of the equations, the constant numbers. This kind of table is called the augmented matrix. The augmented part is that dividing line which divides the two parts of the equation, left side the variables, the right hand side the constants. Okay, we call it the augmented matrix. Okay, here is an example. Take that system of equations here and look at its augmented matrix form. Okay, and for the first example here, a simple example, they have shown every variable x. Every equation has every variable, so it's very easy to see. Okay, these are the coefficients of x, these are the coefficients of y, and so on, right? And every row you can see represents a equation. Okay, the vertical line that separates the numbers are on opposite sides of the equal sign. So this line is the augmenting line. I think in this type format they get condensed. You might want to write them a little away, okay, for clarity. Okay. When we do this, we must use elementary row operations to transform this array into the diagonal form, where only the diagonal has numbers, and that also will be 1, 1, 1. That will be easy to do. But everything else, focus on everything else also. Okay. What do you see? Everything else is 0. Everything else is 0. That is what we try to achieve by using the row operations. And that method, okay, when you do that, that method is called the Gauss-Jordan elimination method. Okay, this is, again, I would say this is the end goal. This is the matrix you want to get at the end. Okay, and this star 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 here will be the solutions of the system. Whatever numbers you get here, this is x, that is y, that's z. Okay, let us let us take that previous system here and we will solve it now. You write this down, okay, and try to follow the logic in every step. So this is the initial matrix, and our goal is to get these to become 0 and 0. Okay, now here's the thing. We proceed one column at a time. That will be the best strategy to apply. Okay, you want to have get in the diagonal form, start do one column at a time, not all at once. Okay, and don't go in a random order because it will get mixed up and there won't be any progress after some steps. So the way to make sure that we are constantly progressing towards the end goal is one column at a time. So I want to, in the first column, I want to set these elements to 0 and 0. How do I start? Um, Again, when I'm solving problems later, I might do a little differently, and I'll explain when I do that and what I'm doing. Here, in the book, in these slides, what they have done is you always make sure that the diagonal element is 1. Okay, and the word they have used, that is used in literature is called pivoting. Not just that, making that 1 and making the remaining element 0 in that column is called pivoting. Okay, that process. And one part of pivoting is making this element 1. When I do, I do the part where these elements become 0. Okay, in when usually I solve systems, these elements will go to 0, but I don't really care about that element becoming 1 initially. I do that at the end. Okay, it's just a question of, as I said, different people could do the um, operations in different order and have the same end result. Okay, all right. Um, Let us follow for now what is done here. This is 1/3. So the first row is divided by 1/3. 1, -2, 3, as you divide by 3, 0. And how does that help? This method has its advantage, okay? Because that element is now 1, let us focus on the first column, right? You might say, why did we do the row operations? We are focusing on the first column, but we need to do row operations. Okay, we don't do column operations. Whatever operation you do has to be done on the entire row. So our goal was to make the element in the first row, the leftmost element in the first row to be 1. Okay, that's what we achieved in that step. Next goal is to make these two elements 0. So what you do one by one, first you add -4 times, or basically you're subtracting, right? I think it's easier to see it that way. You subtract 4 times the first row from the second row, because you have 4 here and you have 1 here. So 4 minus 4 will make it 0, right? That's the goal. So you get that 0. So that gives you the idea. You have -2 here. What do? Add 2 times the first row. Once again, I will emphasize, make sure that you don't do only for that element, right? It's not that only this element becomes 0 here. That R2 minus 4 R1 is done on the rest of the row also. Okay, for example, I will explain one of them. Here it was -6 and you are subtracting. Let's do that calculation here. Okay, -6 minus 4 times R1. So the element in R1 there is -2, right? So -6 minus -4 times -2 becomes +8. So that becomes 2, right? You see that 2 here. Okay. So you do that row operation, that particular row operation on the entire row. Okay. And now the first column is taken care. You focus on the second column. In the second column, first you want to make this element 1. Diagonal. Remember the diagonal is okay. So you divide by half. And once that element has been converted to 1, it's good. Now you shift your focus to the other two elements. That should go to 0. That should go to 0. And how do I do that? -2 there. So add 2 times the second row. -5 here. You are going to, in the next step, you are going to add 5 times the second row. but do the row operations in the entire row every step. Okay. And by that time, now you have converted the second column also. So first column taken care, second column taken care. Focus on the third column. I have -3. So divide by -3, that gives you 1 here. Okay. And when you divide by -3, um, is that a typo here? I'm observing a mistake here. This should be -1 because you're dividing by -3. Okay. And then what do you do? Unless I'm mistaken. Yeah. Okay. And after that, now the next step is to send this to 0. So there is -1. You are going to use the third row. So you add R3. Okay. And here -2. So you add 2 times R3. And that's your diagonal form. And you have your answer here. Okay. And once you have that, you have your answer. So I have not checked the, you can check the values, you can take these values of x, y, and z and plug it in the original equation and verify if that's the actual solution, which I guess probably they should have done, but not done here. That's unfortunate. You can do that. Okay. You check that your answers are correct. There might be some mistake here is what I'm thinking, or it could have been -3 here. So that was still 1. um, we will do our own problems later. Okay, we will be solving problems. So let me not spend time on that. Before being done with this, lecture slide, I will talk about something important here. Yes, which is this. Let me clear out the page. Notice that when you are manipulating the third column, okay, you use the third row to send this also to 0 and that also to 0. For both of them, you use the R3. Observe that. Okay. Before that, when you are trying to mm, make the elements in the second row, again, let me clear out. There are too many things here. Here, when we are focusing on the second column, what did we use? Let me zoom out. We use the second row to make the third row elements, that to 0 and that to 0. For that, we use the second row. In the first column, we use the first row. Remember that. Okay. In each column, whatever is the column number, you use that row number to manipulate the other elements in most normal cases. Okay. Until you get good practice. Later on, you will see, there can be some variations, and I don't have to explain that now. But this is the working method. Initially, these techniques will be useful. Okay, let's look at the summary of the whole discussion. Okay, there are 3 elementary row operations. Let us remember them. What is that? Interchanging rows, multiplying a row by a number, adding one row to another row, and we have noticed that we can combine them. Okay, multiplying a row by a number and adding to another row, we have seen that being done in a single step. Not only that, as you get more practice, you can do more than one row operation in a single step. For example, if you are going to make the second and third element in the first column become 0, you can do that by simply taking you can do both those operations in a single step. Okay. When you get comfortable, do one at a time initially till you get good practice. Okay. And The Gaussian elimination method, okay, is the process which does the sequence of row operations until the solutions can be easily obtained. Um, I'll pause here, and in the next video, I'm going to be working on some solutions, some practice problems, and although we did all three variables examples here, in that video, first I'm going to be discussing some questions, general questions about linear equations and actually two variables. Okay, I will discuss some two variables. I will discuss solving without matrices, the ordinary method, all of that. And then in the subsequent videos, I will be solving three variables systems and also by using matrices. Okay, stay tuned. See you later. Thank you for watching.